Hello all, welcome back to the another lecture. So in this particular lecture, we will see the introduction to silicon carbide devices, right? So in the last lecture, we have seen what is wide bandgap devices, what is the need of wide bandgap devices, what is the motivation to study the wide band devices, what is the motivation to do the characterization, what are the applications of wide bandgap devices, and we have seen the comparison of silicon carbide and GaN devices, right? So in this lecture, we will basically go in much more detail about the silicon carbide device, and we will see a few more things about silicon carbide. So let's get started with this lecture. So introduction to silicon carbide device. So the availability of high quality silicon carbide vapor allow a reasonable yield of large area silicon carbide power devices. Currently 150 millimeter or 6-inch silicon carbide vapor are commercially available. If you have seen the manufacturing of the silicon, right, then the using the wafers only we will produce any device. The same manufacturing technique is available for the silicon carbide also for vapor production, and its availability is also reasonably good. So that's why we can make more devices through the silicon carbide, but it is not mature that much, and that is why there is a need of characterizing this device. So the status of silicon carbide based devices. So what is the status now of the silicon carbide based devices? Like what status I am talking about? How and what people have made through the silicon carbide. So if you see, so some are commercially available devices. Like silicon carbide is a material through which I can make diode, through which I can make MOSFET, IGBT, SGT, anything I can make, right? So what people have made through this particular silicon carbide devices, and this is shown by some commercially line. It is a straight line, and this is a dotted line where the research and development in phase. So SHG, MOSFET, JFET, these all things are basically people have made. So research are going on that, like basically thyristor making, IGBT making, pin diode making, MOSFET making, few different types of MOSFET making. So the research are going on how we can make this, and these are not commercially available, right? So this is the point I have told you, that what is silicon carbide devices, their wafers are available and what people have made through this, and this is the state of silicon carbide as on today. So next thing we will see the structures of silicon carbide MOSFET. That, like, if you see the structure, you can find out, yeah, this is just a similar kind of structure as a MOSFET, right? But the material is different. We are not material side people, so we will not talk too much about this. So this is a sort of structure a silicon carbide MOSFET have. So there are the two structure I have shown. One is a planar DMOS structure and another is a trench structure. So you just see this. We are a power electronics engineer. We are much more interested in knowing that what are the losses in the device. If we have some device, what are the characterization, what is its VI characteristics and all. We are much more interested in this part, right? How the structure have made and all. We are not too much of interested in it. This is a part of VLSI people and material science people, right? So this is a just to show you that how the structure of silicon carbide MOSFET is. I have just added this picture for you. Same silicon carbide N channel IGBT and silicon carbide P channel IGBT. This is the structure: P drip layer, P drip layer, N P and N drip layer. So all these things are there: substrate, collector. These are the terminals of the IGBT. So all these things you know already, right? Just to show you the structure, I have added this. Now important slide I'm talking about, that is material property comparison between silicon and silicon carbide. So this thing we have already see the breakdown of the electric field, millivolt per centimeter. So for silica it is a 0.3, for silicon carbide 2.8. So very high breakdown strength, right? Second most important thing is basically it's a lower on resistance. If you see this silicon substrate and silicon carbide substrate, so if you see this, you can find that the lower resistance, like if it has a resistance of 1 ohm, then silicon carbide has a resistance of 1 by 300 to 1 by 1000 times. So very less resistance value silicon carbide has, on state resistance value. So we generally talked about the turn on losses. So using during the turn on losses, this on state resistance, the current flowing through this on state resistance will cause the losses in the device. But if we see the silicon carbide device, the on state resistance value is very low, so very less losses and our efficiency will be increased. So another thing I wanted to say is, basically for any particular device there is a body diode available. You know body diode, so that is the inherent diode available with the devices, right? So, and this body diode have some reverse recovery losses. You know about reverse recovery losses in diode. So the same thing is happening here. So during the process of on or off, these losses will happen in this body diode. But if you see the body diode of silicon carbide or even a GaN device, so it has negligible basically reverse recovery losses. We will see this in the data sheet. Very negligible, I am talking about almost zero reverse recovery losses silicon carbide and GaN devices have. So that is the advantages we have when we go for the wide band gap devices. So from this slide, I guess things are pretty much clear that why we are going for this devices. We will see in the data sheet actual numbers, how much difference, and we will compare. Okay, so till this point I guess clear everything. Now next thing is basically the specific on resistance as a function of the breakdown voltage. So you see that how much on state resistance it has. It is in, basically if you see, so very less resistance value it has, like at 3.3 kilovolt, what is the value, and also basically very less resistance value it will show, and that is the beauty. It is in the milliohms. You can see 1 milliohm at 900, 10 milliohm, 100 milliohm at 10 kilovolts. So very less on state resistance, and because of this very less losses will be happening, right? So I guess this is clear to you. Now you have the question that, okay, we have seen the structure of silicon carbide, but how we can represent it? So representation is very simple. Generally whatever the symbolic representation for our basic devices are, the same kind of symbols we will generally prefer for silicon carbide. Just we will mention it as it is a silicon carbide device, and terminals are the same. I have told you that we can make diode, we can make IGBT, we can make anything, right? So this is the ST power silicon carbide MOSFET. Again ST power silicon carbide diode. So schematic symbolically wise it is same. There is no much difference, right? So they are same. Second thing is, this point I have already told you, this is our key point, that silicon carbide excels in high voltage and high power application like EV, inverter, renewable energy system, etc., where the switching speed of hundreds of kilohertz, right? So they are use hundreds of kilohertz switching frequency, but not go in megahertz, but they have very high voltage application, right, and high power application, where this devices we can use. So we will move forward. So another key concept I am going to give you. What is that concept? If you see any device, okay, so any device, how any device will turn on? Any device will turn on when we give a gate pulse to it, right? When we give a gate pulse to it, any device will turn on. So what is this gate pulse? Gate pulse is just a basically on and off pulse, which is we are going to give on through the driver. So we have the gate driver available with us, and through the gate driver we will give the gate pulses. Now you see this capacitance CGD, CGS and CDS. These are the if you see the device, these capacitances are not there, but through this capacitance is only, when this capacitor will charge, that time only the current will start flowing through this and it will trigger it and turn on the device. So this capacitance play a very important role in any particular device. So we will see in the data sheet, they will mention like COSS. What is COSS? It is a output capacitance. Output capacitance is a combination of CDS plus CGD. CISS. What is CISS? CISS is a input capacitance. It is a combination of CGS. What is CGS? CGS plus CGD. So these two capacitance combinedly called as a input capacitance. And another capacitance is there, that is CRSS. What is CRSS? it is a reverse transfer capacitance. So these three capacitance are there. So you maybe know this concept that this capacitance exists in any device, and with the charging of this capacitance and discharging of this capacitance, the current will flow through the gate driver, through the gate terminal, and it will turn on or turn off the device. So this is very important concept. We will see this term COSS, CISS, CRSS in the our data sheet. With this only we will come to know that how much voltage I want to give to my gate terminal, so that I can charge this in very quick time, and basically it will how much basically it can be stay, and this how much time it will take to discharge. So this will things we have to look for when we design a basically gate driver. So these are very important parameter. So till this point I guess everything is clear. Now we will move forward. So who manufacture the silicon carbide? So there are the different manufacturers available who can manufacture the silicon carbide, like the Infineon are there, Mitsubishi, Roham, Semi South, IR, ST Microelectronics, and more manufacturers are there who manufacture the silicon carbide, IGBT, MOSFET, and so many other power electronic switches. So if you want to buy, go through the first data sheet, read the data sheet carefully, and then according to your requirement you can order any switch, right? So I have just told you that who manufactures, so you can see, just go and download any one of the data sheet from any one of the manufacturer and just see what exactly it is. We will see basically the data sheet, what are the key important point we have to look in the data sheet and all. So we will go further. So what are the challenges of silicon carbide? So we have seen that silicon carbide is very good and all, but what are the challenges we will face when we will go to use the silicon carbide? So I will take a bit of time to explain this slide, because this slide is very important. Our entire course is based on this slide only. So we will go one by one. Just listen to me carefully. First point is the field reliability of silicon carbide devices must be demonstrated for various applications. Like when we see the data sheet manufacturer must say that these devices are applicable to which application, because that is the thing. If we know that okay, this device is manufactured for this particular application, then we can go to use it. Otherwise how we can use it, right? We have to characterize it, that is fine, but we need much more data available, then only we can go for using it in a particular application. Second one is manufacturing process need to be improved for better cost of silicon carbide device. So these devices are bit of costly, right? So because they are providing they provide you the very good advantages, and because of that the cost is also increased. But if we work on manufacturing process, then maybe we can decrease its cost. So people are working on its manufacturing process so that the cost will decrease. Third point is silicon carbide devices switch much faster than the silicon devices, which poses a challenge to a gate driver design. That is a third important point, and in this course we will see how to design the gate driver for the wide band gap devices. Like whatever the gate driver available with us, they are for silicon. We cannot directly use them for wide band gap devices like silicon carbide and GaN. We have to do something, then only we can use this. So for gate driver also it is bit of challenge to turn on and turn off this silicon carbide. I will show you in the data sheet that if you see the silicon carbide data sheet, it's a VGS, that is VGS. What is VGS? Gate to source voltage, which is required. VGS, right? So VGS value is, I will show you in data sheet. So if you see, VGS value is always from 0 to some positive value if we see for the silicon devices. But if you see for the silicon carbide devices, it is start from some negative value -5 to some +20 volts. So you can think from that the gate driver, we need to provide the negative supply voltage when we have to turn on the silicon carbide devices, right? So negative VGS is required when we go for silicon carbide. So this is the another thing. But we don't have the gate driver available like this, right? So supplying the negative voltage -5 to +15 +20 volt is again a challenge, because what we have generally do for silicon devices, we will give 0 to 10 volt, 0 to 20 volt, this kind of voltage we apply generally, right? So this is the challenge which is facing by the gate driver circuit, and how to design this, that we will see in this course. Third one is the innovative EMI filter design need to be investigated. So whatever the EMI filter as of now are designed, they are for silicon based devices. So we have to look for this also, that how we can improve our EMI filter, because EMI, EMC, these two are the standards which we have to follow before putting any device commercially. So we have to look for this also. Then fourth one is the novel system layout with minimized consumption loop criteria, including both the silicon carbide device package and system busbar layout. Like I wanted to tell you from this, the parasitic effect. So we have the process for designing the layout, designing the PCB for silicon based devices mostly, and because of this we have to look for some alternative. Now we are using a wide bandgap devices, so same process we cannot directly implement, we have to look for something. Fourth, another point is the silicon, the smaller die size of silicon carbide chips and corresponding higher low density open the new design challenge for thermal measurement strategies. So if you see, if you have bought some silicon carbide or silicon device, you just see and compare its size. I have already told you size of these silicon carbide chips are very small, and if you try to provide the some thermal heat sink and all protection to it, it is very difficult to implement this, because these chips are very small, and if you want to put heatsink, it's really difficult task on PCB. So this is the another challenge. Another point is the high temperature operation capability of silicon carbide power devices require innovations in peripheral components such as high temperature capacitors, packages, control electronics, gate driver and sensor. What I wanted to say from this point, like I told you that okay, what my silicon devices are there, they will operate at some two particular temperature level. With the advancement in the silicon carbide device, I can improve my temperature range. I can use very high temperature applications, and I can use my silicon carbide or gallium nitride devices. But what about the other components which are present in the circuit, like the capacitors, control electronics equipment, gate driver and all? They are not capable for the high temperature application. They are there with respect to the silicon. So we need to find out some other alternative, like whatever the capacitor we are using, that is up to some particular temperature level. If we use it along with the silicon carbide, we need to increase our temperature level. Otherwise, how we can implement it in circuit, right? And last point is, for many potential silicon carbide user, the high non-recurring engineering cost is also concern, because the limited knowledge of these devices. So these devices, I already told you, these devices are immature. So you cannot directly take these devices and use in your application. You have to do some testing and all before implementing this device in particular application. So if you don't have that equipment available with you, how you can go directly and use these devices? So these are the various challenges which we have seen, and based on these challenges only we have to discuss our entire course. We will, based on these challenges only, we will look for the gate driver design, we will look for the EMI EMC design, we will look for the layout design, and we will look for this heatsink design, that how we can design the heatsink for our this thing and all. So all these things we are going to cover in this course. So this is very important slide. So this challenges, by looking at these challenges only we will go further. So now we will see the data sheet of silicon MOSFET. Then firstly we will see the data sheet of silicon MOSFET, and we will compare it with the silicon carbide MOSFET. So you see the device data sheet of Vishay power MOSFET I am just taking. So what is the VDS? And drain to sense source is 500 volt. So you can use this particular switch up to 500 volt. What is RDS on state resistance is 0.27. What is the gate charges? QG maximum. What is the gate charges? So this, how these gate charges are related, you know this relation, Q equal to CV, Q equal to CV. So from this you should know about the, you have your voltage, how much voltage is required, and you have your charge. So you can easily find out what is the value of the capacitance. So this capacitance, so for that they have given this thing. So another they have given something, and this is the symbol they will give that, and this is the three terminal gate, source and drain is there. So this is how any particular device is there. Now what are the important thing we have to look? So this looks this particular thing. So drain to source voltage, I have told you that this is the maximum voltage you can use this device up to. So up to 500 volt application you can use this device. Then gate to source voltage, so plus minus 20 volt. So it require only 20 volt. So if you start with the 0 to 20 volt, that is fine. So I don't need, it is mentioned here plus minus 20 volt. Some may sometime minus 20 to 0. Likewise also some people will give negative gate pulse. So that is people will sometime do, but generally we will give from 0 to 20 volt. So that is the gate to source voltage. So we don't have to give any negative gate pulse. Another things are also mentioned here. So whatever the key peak diode recovery, so reverse recovery time of the diode recovery dV by dt, it is mentioned 3.5, which is very high, and it will cause too much of losses in our system. Another important thing is I have talked about the input capacitance CISS. CISS is combination of what? COSS is combination of what? Reverse transfer capacitance. All these things are mentioned. What is the rise time for this device, fall time of the device? So using this thing we can actually calculate the turn on, turn off losses, conduction losses, switching losses. So we have a rough idea about the efficiency of this device. Okay, so these are the some important things which you have to look when you see any data sheet. Now we will see the data sheet of silicon carbide MOSFET. So when you go for seeing the silicon carbide MOSFET data sheet, you just see, you see the VDSS. So drain to source voltage is 1200 volt. So it is, we can use up to the 1200 volt. It's a very far as compared to silicon, but still it's RDS on. You see 160 milliohm, very less RDS on you can see here. So very less losses will happen, and because of this efficiency is automatically improve. Another thing, pulse, if you see the gate to source volt, so gate to source voltage, so minus 4 to plus 20 volt. So this is what I said, ki we need a negative gate pulse when we have to provide the gate to the our silicon carbide device or GaN devices. So this is what I wanted to say. So negative gate pulse providing itself is a big challenge. So that we have to learn how this we will demonstrate in the LT spice. Then temperature and all other things are mentioned. What other thing important for here is on state resistance. I have already shown gate input resistance. If you see, it is 18 ohm. So that is different thing. What when we connect our gate driver to the gate terminal, that time you have to put some resistance. So that is the resistance. This is. So another few important terminologies are, what is it, input capacitance, output capacitance. You just take the screenshot of that and they see. So if you see and compare the what is the where the input capacitance, output capacitance, reverse transfer capacitance are more and where are less. Another thing is charges and rise time, fall time. So you will find that the overall loss in the system, you see the turn on switching loss, turn off switching loss, these are very less as compared to the silicon. So thanks for the watching this video. So in the next class we will see the gallium nitride device. So in the same way we will see the gallium nitride, how the gallium nitride, what are the challenges when we implement the gallium nitride, and we will compare the data sheet of silicon and gallium nitride, so that we will get a broader idea about what is wide band gap devices, how the silicon carbide and how the gallium nitride is there. So once we finish with this, then we will go for the characterization of this device. So what different tests we will perform, and how to get the data from them and all. So we will see later. So thanks.